Ooh, right.
Right, okay. That's some quiet, please. Okay, the last day we finished off at this slide here. And today we're going to carry on from, we talked about the Beer-Lambert law on Tuesday. And that was the rule that governed the intensity of the bands in a UV or visible spectrum. And today we're going to move on a little bit to talk about the origin of these bands. Where do these bands come from? And UV visible bands are usually due to electronic transitions. So to understand the electronic transitions, we're going to have to understand a little bit more about electronic structure of the molecules that we're looking at. So to understand it, you have to know a little bit about molecular orbital theory. We're going to be talking about molecules, and we need to know a little bit about molecular orbital theory. Now, I'm not too sure how much background you have in molecular orbital theory. Have you done linear combinations of atomic orbitals before? So you did that in the first semester, did you? Right, okay. Okay, so we can go fairly quickly through this. But just to recap, you have the idea of a molecular orbitals is that you have two atomic orbitals. So here the simplest case is hydrogen. So you have the 1s orbitals, and they combine to give you kind of push them together, if you like, to give you two molecular orbitals. And the idea behind all of these is that they, I hope you now realize that electrons don't reside in boxes. Sometimes students from school especially have this idea that orbitals are little boxes and the electrons are little thumbtacks that reside in them. These are just mathematical descriptions, and they're waves. That's why I put this plus sign here. And these come from the solution of the Schrödinger equation for the hydrogen atom. So this represents a three-dimensional, this spherical shape for an s orbital is a three-dimensional representation of the wave function that comes out of the Schrödinger equation. So they've got nothing to do with boxes. So, and like any wave, like if you have a sine, a typical wave that you're familiar with, you have positive and negative parts, and the same thing for these. That's why we put plus and minus on these orbitals sometimes. So what they can do then, waves can combine together, and we know that if you get constructive interference, you get increased amplitude for the wave, and therefore in these two 1s orbitals come together, and you get constructive interference, and the amplitude, the combined amplitude is greater. So that's what's called a bonding molecular orbital. And when they come together for the sigma, for the 1s, we call that a sigma orbital. But you can also add these together. So here you're adding plus plus, but you can also say plus minus. So you put a minus one here, and then you get this antibonding combination. Because the two waves destructively interfere here in the middle. You have the plus and the negative parts together. So they cancel out, and you get an antibonding combination. So this one is more stable, the bonding, because it's got electron, here you have the two nuclei, they're positive charged, and here you've got electron density here in the middle. And that's a stable situation, and that electron density can spread out, so that's a stable situation. Here, you have no electron density in the middle between the two nuclei, so that's an unstable situation. You've got two positive charges, and none of the electron density to shield them from each other. And also, there is a much more confined space, if you like, for the electron density. So that's the basic principles of molecular orbital theory. You have a bonding and an antibonding combination. And here I just elaborate on this for your notes. So then this is just an energy level diagram. The way you usually write this is you have an energy level diagram. Here you have your two atomic orbitals on each side. And then you have a lower energy bonding molecular orbital, and you have a higher energy antibonding molecular orbital. And then if you want to say this is a hydrogen, you'd have one electron on each of the hydrogens, and then you fill them up just like you learned in school. You fill up each orbital, like each atomic orbital, you put 2 electrons in, and the 2 electrons have to be of opposite spin. And each orbital can only accommodate two electrons. Okay. So here I've just summarized it for you, again for your notes, what I've been talking about. So you get close enough, you get the atomic orbitals, they reshape to molecular orbitals. And then you have some key points here. So the number of molecular orbitals is going to be equal to the number of atomic orbitals. So if you have altogether 6 atomic orbitals, you're going to get 6 molecular orbitals. And then you have the bonding, which is the lower energy one, and the antibonding, which is the higher energy one. And the reason why it's higher energy and lower energy, we've just gone through. The electrons enter the lowest orbital first, and then the maximum number of electrons is 2, and this is due to the Pauli exclusion principle. And then sometimes if you have equal energy orbitals, say you had what we call degenerate orbitals. So here's our energy like this. Now the electrons, as you learned in school for p orbitals, they fill these each up separately first, because that's a lower energy situation than pairing up in the same orbital. So when you say you had 3 degenerate orbitals like that, then if you had another electron, they fill up, the other one would fill up and pair up like that, and then they'd have to go up to the next level. Right, so there, what we've talked about is antibonding orbitals, but what we need to understand is that in certain molecules as well, you have what are called non-bonding orbitals. And these are orbitals that are usually the same as in the atom. So you have two atoms coming together, say in the simplest case, and you have an orbital on one that has no counterpart, if you like, to bond with on the other one. So it stays, it doesn't form an antibonding orbital or a bonding orbital. It just stays non-bonding. So it's an orbital that isn't involved in bonding. It just is the same as it would be, pretty much, the first approximation, as it would be in the atomic system. Okay. So then we have the p atomic orbital. So we've looked at the sigma 1s at this stage, but you also have the p orbitals. So and you go to the second shell, you have the p orbitals, and here we have how they combine. Now there's two different types of combinations. You can get the sigma overlap, which is the same as we got for the SS overlap already, and that's when the two orbitals point at each other. And by definition, that's usually for the PZ. So we could imagine this is a carbon atom here, and that's a carbon atom there. And then we define our axis system, say that this is that's the Z-axis. So you have, again, you have this, excuse me, the p orbitals, as you know, have positive and negative phases. So they can combine, so you can combine a situation, so you switch this one over from the way it's written, you'd have the positive here. So now you get a positive overlap. Again, they're waves, so it's constructive interference. So you get a build-up of electron density between the nuclei. And that's a bonding situation. If you flick it over like it's drawn here, you have positive and negative, so you get interference, destructive interference between the two waves, and therefore you get no electron density between the nuclei. So this situation here is a stable situation compared with the separated orbitals, and this is a destabilized situation. So this is an this is a bonding sigma orbital, and this is an antibonding sigma star orbital. And of course, you have got you all know that you've got, in addition to the PZ, you've got the PX orbitals, and you've got the PY orbitals. And they undergo a different type of bonding. They undergo what we call pi bonding. Because these now, instead of this head-on collision that's happening here between the PZ orbitals, you have side-by-side interaction. So again, you can imagine a situation where you get the two phases together. So you've got a plus together, then you'd get a nice bonding situation on the bottom there. And likewise, the two negative lobes that overlap, and you get again, you get constructive interference. But if you flick this orbital over, say you flick this one over, so you have now the positive side up here, and the negative side down here, then you have positive against negative, and that's destructive interference. So now you have, again, an absence of electron density in the middle. And we classify them as pi and sorry, the definition comes from the symmetry of these orbitals, which involves symmetry theory, which you don't need to worry about. But usually sigma orbitals have electron density along the internuclear axis, if you like. That's the definition of a sigma. And you can see for the pi orbitals here, they've got no electron density. Even the bonding ones have got no electron density along that internuclear axis. So that's so this is a sigma, and this is a pi. And that's for the px, and of course the py is perpendicular to that. It's, if you like, it's coming out at the projector from us, and you get exactly the same type of interactions. You can get constructive overlap here, giving you a bonding orbital, and you can get destructive, giving you an antibonding orbital. Okay, so again, for your notes, this is pretty much covered here. And then you have this is a sigma bond and a bond formed by the p orbitals overlapping side by side. That's a pi bond. And then we have what are called non-bonding orbitals as well in certain molecules. And let's just look at a situation where you have a a non-bonding situation. Here we have a molecular. We've been talking about the CO chromophore is quite important in lots of biological molecules. You have the CO, of course, in the peptide bond, and you also have it in a lot of molecules of biological relevance. And we'll be talking about some examples later on. But here we have a molecular orbital diagram for the CO molecule. So again, it's drawn in the familiar pattern. You have here on this side, you would have the energy. So the energy is going up there. So you have the carbon 2s orbital, and you have the carbon 2p orbitals. So of course we don't include the 1s orbital. Why do you think we don't include the 1s orbital? Any idea? Sorry? They're not valence electrons, yes, so they won't be involved in the bonding. So something like the 1s orbital is core, and that will be pretty much for, say, something like CO, the 1s orbital in the CO molecule will be pretty much similar to what it is in the isolated carbon atom. Okay, so on this side, you have the carbon, and here you have the oxygen orbitals. Again, you have the 2s and the oxygen atoms. And what you'll notice is, as is drawn in this slide here, the oxygen orbitals are slightly lower in energy than the carbon orbitals. And does anybody understand why that's the situation? Why have I drawn them like that? Okay, right. Well, which is the most electronegative atom? Oxygen or carbon? Sorry? Oxygen, yeah. So oxygen pulls its electrons tighter to itself because it's got a higher charge. It's further up on the periodic table, so it's got a higher charge. So it pulls its electrons closer to itself. So that means that the electrons in especially in the 2s orbital of oxygen, are lower in energy. It's a more stable situation. So stability means lower in energy. So when you're drawing a molecular orbital diagram like this, you have to draw it. It should be schematically shown lower in energy than the carbon atom. The same thing, not as much for the 2p, but the 2p will also be at a lower energy. The 2p electrons in oxygen will be at a lower energy than the carbon 2p electrons. So that's why they're drawn lower. And again, based on what we've done just 2 minutes ago and what you've learned previously, you should form a sigma bonding orbital and a sigma antibonding orbital from the 2s orbitals of the carbon and the oxygen. And what you'll notice here is that this is much closer. The bonding orbital is closer in energy to the oxygen. And that's what happens when you've got two different electronegative atoms combining. The bonding orbital is composed mainly of the oxygen. The oxygen is a greater contribution, whereas the antibonding will have a greater contribution from the carbon. Okay, so that's the 2s, and then you have the 2p, and you have here a complex series of lines which we're not going to go into in much detail, but basically you have the same type of bonding that we talked about for the p orbitals. You have here, we see just 2 pi orbitals of the same energy, the degenerate, and these are the side-by-side overlap of the p orbitals on the carbon and the oxygen. And you also have this one here, the sigma, and that's the pz, or mainly due to the pz combination, the sigma bond formed between the p orbitals. Now what happens in this molecule CO is that this sigma is pushed up quite a bit. Usually this is down here, but in CO, for a variety of reasons, it's pushed up quite a bit. And essentially, it's very close, if you like, to the energy of the oxygen atomic orbital. So when you have an orbital like that that's very close to the energy of the atomic orbitals, then usually we would call this a non-bonding orbital, or NB for non-bonding. Okay? So that's one. There's other different types. Sometimes you have no counterpart over here, and you'll get orbitals there for different molecules, not for the CO molecule. But a non-bonding orbital is usually around the energy of the isolated atoms. Okay, so that's the background theory of the molecular orbitals, and we need that, as we'll see in a minute, to understand the UV visible spectroscopy. So what you have in a typical molecule is you have sigma bonding orbitals, like we've seen. You have pi bonding, and then you have non-bonding. And then this is called the ground state, if you like. So if you fill up electrons, let's just do it, say this is all paired up. See, that's something like that. Now, what happens in UV visible spectroscopy is that you get promotion usually. You get transitions occurring. So you might get a non-bonding orbital going to a pi star orbital, or you could get a pi bonding going to a pi star, or you could get sigma to sigma. So here is the energy between them. So what you should see immediately from this is that the gap between the in and the pi star is the smallest, and next you have the pi to the pi star, and then the sigma to the sigma star, or the sigma to the pi star is quite a large energy gap. So when we're talking about transitions occurring in UV visible spectroscopy, we're talking about these kind of electronic transitions. So here I just put in the delta E. And what we'll find, we'll talk a bit more about this in a moment, is that in the UV visible range, we talked about the electromagnetic spectrum on last Tuesday, is the range, that's 700 down to about down to about 400 for the visible, and then you have 400 to 200 for the UV. That's about the range of these transitions here. The transition between a non-bonding and a pi star orbital, and also the transition between a pi bonding and a pi star antibonding orbital. So if you irradiate your molecule with UV visible light, then you can induce these transitions. What you find is sigma to sigma transitions, or sigma to pi transitions, the gap is too big. That would fall at higher energy regions of the electromagnetic spectrum, up in the X-ray, gamma ray region. But UV visible light is not able to excite these transitions. So when you're talking about UV visible transition of organic or biochemical molecules, you're usually talking about two types of transition. You're talking about non-bonding into pi star, non-bonding to pi antibonding transitions, or you're talking about pi to pi star transitions. Right, so this here we just said, so visible light is going to 400 to 750, and as we said there, UV is considered about 200 to 400. So the energy of the UV visible region, as I said, is insufficient to promote electrons from signal. So that gap is too big. But it is in the region covered with the pi electrons and the non-bonding in electrons. And we see therefore two types of transitions. You see into pi star, which is this one here, and you see pi to pi star. Okay. Right, okay, so the normal configuration of a molecule, if we go back here where I did it here, we had the electrons filling up the bonding levels, is the ground state. So what you have is two important orbitals. You have what was called the HOMO and the LUMO. And the HOMO is short for highest occupied molecular orbital, and the LUMO is the lowest unoccupied molecular orbital. So again, if you draw, so you had energy levels like this. Here you have your energy. You fill them up in pairs. And say that's it. This one here is the HOMO. And this one here is the LUMO. All right. And when we're talking about electronic transitions in UV visible region, we're talking about transitions like that. And usually the HOMO is either a non-bonding orbital or it's a pi orbital. So if you change the energy levels, this thing here that I've drawn with the arrow is a transition. And the lowest energy transition involves transition between the HOMO and the the LUMO orbitals. Now we're not going to get into this in great detail, but when you cause an electronic transition like this, you move an electron from, say, a HOMO to a LUMO. What you also tend to do, we're going to talk about vibrational transitions next week, is you also have a change in the vibrational levels. And again, just for those of you interested, you would have a, sorry, let's just draw it here a bit. Right, so in reality you would have something like this for electronic transition. This is called a potential energy surface, and you have a number of vibrational states like that. Again, I'm not going to, this is just in case people are interested. You cause an electronic transition in between these levels. So you might start off in these lines are the vibrational states of the molecule. You might start off in the lowest vibrational state, but when you cause a transition to the excited state, sometimes you end up in an excited vibrational state. There's no guarantee that the vibrational states are lined up exactly. So what that causes then, sometimes you get fine structure on your band, your UV band, and that's due to this vibrational energy. So that's going into it in a little bit more detail. Okay, so we'll talk about vibrations next week, and then excited states are very short. So you cause the excitation, your molecules there, the UV visible light comes in, it causes the transition, and then it passes on. Of course, then the molecule is excited, so it will relax down to the ground state after that. And there's various ways in which you can relax. You have various types of fluorescence again, which we won't be covering. Okay. So again, so this is just a summary really of it. You have into pi star, pi to pi star. Again, only compounds. Well, organic compounds anyway, with pi electrons or non-bonded electrons usually produce UV visible spectra. And another key point here, when we'll look at some examples in a minute, and you'll have some examples in the workshop today, is that n to pi star is less than the pi to pi star. So you just go back to here we have an n to pi star, so that gap there is smaller, if you like, than the pi to pi star. So what we're trying to do in electronic spectroscopy is we'd like to identify which is which. And as we'll see in a minute, one way to identify it is the fact that the energy of the n to pi star is less than the energy for the transition of the pi to pi star. All right, so also we're usually going to talk about, when we're talking about UV visible spectroscopy, we talk in terms of wavelength, nanometers, and you've got to remember this fundamental equation, Planck's equation from the last day, that E is equal to hc over lambda, or E is inversely proportional to the wavelength. So the higher the energy, the shorter the wavelength, and the lower the energy, the longer the wavelength. Right. So let's look at an example here. So you have the, here we have a very simple molecule, acetone. But it's got the carbonyl chromophore, which is present in a lot of biological molecules. And here you have its UV spectrum. So what you have here is you have a band at, I give the values here, the band at 187 nanometers, which is this one. And then you also have a band at 270 nanometers. Okay. And what you generally note in UV spectroscopy is you give the what you call the lambda max, and that's lambda max. Just you have a peak like this, and of course the peak covers a range of wavelength, and you take the peak, the value at the maximum part in that peak. So that's your lambda max. And when you measure that for acetone, it's 1870 and 270 nanometers. So acetone is mainly, sorry, it's got pi and it's got non-bonded electrons, and the non-bonded electron is similar to the CO molecule that we've got, because it's got this CO group, hasn't it? So it's similar to that, and therefore there's two possible transitions. So you have the into pi star, which we show here, and you have the pi to pi star, which is this one here. So now you have to work out which band is which. It's a simple. Right. So what you know is that the lower the energy, the longer the lambda. So the largest lambda here is 270. So you know that that's the lowest energy band. So you know that that corresponds to the into pi star, because that's going to be the lowest energy. So you know that's the into pi star, and the 1870 is going to be the pi to pi star. So that's the kind of analysis you need to do with these seven molecules. Right. So we've defined the pi to pi star here, and we've defined the into pi star. And the next thing you're interested in two aspects in spectroscopy. You're interested in the position of the bands. That will give you the energy for that transition. But you're also, in many cases, interested in the intensity of the bands. And the intensity means the height here, if you like, of the band. And what you what you can see here is that the pi to pi star band is much more intense than the into pi star band. And what you've got to work out is why is this? Because this is also a very good way in identifying bands. If you've got more complex molecules, then there's clearly a difference between into pi star and pi to pi star. And the reason for this is that into pi star transitions, you have lone pair electrons, and these are usually concentrated in a different region. So say the CO molecule, you have lone pair electrons on the oxygens, maybe on the carbon as well. And these are concentrated in a different region of space from the pi electrons, because the pi electrons, as you see here, are in this region. So the pi and pi star electrons are in the same region of space, if you like, for the molecule. And therefore, what you find is you work out transition probability theory, is that this transition, pi to pi star, is more probable. It's more allowed. This comes, again, from the quantum mechanics involved, is that you find that certain transitions are more allowed than other ones. And what you find is that pi to pi star transitions are more allowed, and part of the reason is that they're in the same region of space. So that electron is quite allowed, whereas the into pi star transition, the energy gap is right for it to occur, but it's not as allowed, if you like. One reason is because the electrons are in a different region of space, and therefore the into pi star transition is less probable. So what that means is that into pi star transitions are, the bands due to them in the UV visible spectra are much less intense than the pi to pi star. So here we just again summarize this, so that although the into pi stars occur at lower energy, they're less probable. So here, if you could, there's a number of ways you could think about this. One way is you have a photon coming in, and if it's less probable, it must encounter many more molecules, if you like, before it's absorbed than a pi to pi star photon. All right, so it's not going to be absorbed as well as the pi to pi star. And then the difference shows up experimentally as an intensity difference. So pi to pi star transitions are generally much more intense than into pi star absorption. So this is the way you identify them. So there's a difference in energy, and also now there's a difference in the intensity. So if you're asked to identify them in a molecule, you can do that. So here we just say that in a more quantitative way, it's about 2 to 3 orders of magnitude difference in the intensity. Right, so that's just for the simple acetone molecule, which we show here again. And what you have, of course, in organic molecules, biological molecules, you have more extended conjugation systems. You have aromatic rings and double bonds and so forth. So you need to have some idea of how that affects the position of these bands. So the simplest one you can look at is you can look at your acetone again. We know the lambda max is at 187 and 270 nanometers. We've assigned these to this is to the end, to pi star, and then the higher energy one, the lower wavelength one, is assigned to the pi to pi star, and there's a difference in intensity. And what you find for this one, though, which is a very similar molecule, this is methyl vinyl quinone, you just added another CH2 here. And when you look at the UV visible spectrum of this, you find that these two bands again occur, but now they've moved to higher wavelength or lower energy. So what the reason for this is that when you have a pi bond here in the carbonyl and you have a pi bond here. So the pi orbitals aren't just composed of this C double bond O component for this. You get some mixing into the pi orbitals of this CH2 group as well. So what you have, what you call your extended conjugation. And when you get a more extensive pi system of conjugate double bonds, what you find is both the into pi star and the pi to pi star transitions occur at a longer wavelength. And what's basically happening is you have a decrease in the energy gap. So the more extended the system, the electron spreads out more, and what mainly happens is the energy of the pi star orbital comes down quite a bit. So you have represented here. Here you have without conjugation, and here you have it. Here you have it with conjugation. And now the gap here is smaller. So if the gap is smaller, the pi star has come down, then this is the pi to pi star transition. That will occur at a lower energy and occur at a longer wavelength. And also the same, of course, occurs for the N to pi star. Because the pi star has come down, so the N is, say, somewhere here. So now this gap has dropped as well. So what the effect of conjugation usually is to increase the wavelength of the UV visible band. Right, so again, summarizing what I just said for your notes is that the conjugation decreases the energy gap between the HOMO and LUMO, and therefore you need less energy for electronic transitions. So if you have less energy, it means the UV bands occur at longer wavelengths. And then you have example, if you have, if a compound has enough double bonds, it'll absorb visible light in the visible region. So if we look back at these transitions here, we're talking about 187 to 270 nanometers. Now acetone is colorless because it's got no transitions in the visible. The visible region goes from about 400 up to 700. So these all lie in the UV region. So you don't get any absorption from the visible spectrum, so it's colorless. Likewise for this compound here, I've never seen it, but it's going to be colorless as well, because these transitions 219 and 324 nanometers, they're in the UV region. So you're not taking any, abstracting any colors from the visible spectrum, so it's going to be a colorless. But as we mentioned here, as you go up and get further along, say you had the simplest one would be 18, and then you might have conjugated systems like that. And you can actually show it with these different forms of double bonds, that as you increase the number of double bonds, you start to push this band, UV visible band, higher and higher wavelengths. And basically what you're doing is you're pushing it towards the visible region of the spectrum. And the best example of this then is beta carotene, which is present in carrots, and you all know that's what gives the color to carrots, or tomatoes as well apparently. And what that is then, well, I think we have a picture of it here. Yeah. So here you have beta carotene. I've got a few groups on the end, but what you can see here is it's mainly got a lot of double bonds, bond conjugation. So here we've increased the conjugation, so we've decreased that gap between the pi. There's a pi and pi star transition here. You've decreased that gap quite a lot. So now you've pushed it up to 455 nanometers. So 455 nanometers, of course, is just here in the spectrum here. You show the UV visible spectrum for beta carotene, and you can see that its main band here is, well, it occurs about 455, but then if you impose the spectrum, the visible spectrum, on it, you can see that it's absorbing here in the blue and the green region. So the idea of a color of something is that you're absorbing in the blue-green region, so that's absorbed, and the light that comes out, which you see, is going to be the red-yellow. Okay? So that gives then you the color for the beta carotene. Okay. Right. So you've got a lot of this type of system in biological systems, and perhaps the best example is chlorophyll A, which occurs, as you all know, in green plants. And of course, if you do the absorption spectrum of chlorophyll A, you get two bands in the visible region. And of course, the reason is here it's not. We talked about beta carotene. It was a linear system, but chlorophyll A is a ring system, but it's just got rings of double. These are all alternating double bonds. So it's got a conjugated ring system of double bonds, and therefore you get pi to pi star transitions. And because it's a conjugated system, the pi to pi star transitions occur in the visible region of the spectrum. And here in chlorophyll A, you get two bands in the visible region of the spectrum. And here what we've done is we've superimposed the spectrum onto it again. You know, the visible spectrum is composed of the colors of the spectrum. So you can see that one band here absorbs strongly in the blue region of the spectrum, and you have another band here that absorbs in the red region of the spectrum. So what's left when these are absorbed is the green region of the spectrum. So we all know that chlorophyll is green. And that's the reason. Okay, so there's a workshop on. So I'm going to finish fairly early because we've got to get to the workshop, and you'll have some examples to look at on this. I just want to check on one. All right, so just to follow, because we've got about 7 or 8 about 7 or 8 questions in the workshop, so you won't be able to get through them all. But just one of them is on question 6. It was very close to what we're talking about here, and I just want to. It's just a nice example of what we're doing. So you have tryptophan, phenylalanine, and acetone, which we've talked about, and they all absorb in this region. And you were asked in this question, the lambda max and the molar absorption coefficient are given below, and you're asked to comment on the results. So it's very much based on what we've done here. You have tryptophan 280, and again what we're talking about is the into pi star transitions. So what's the main thing here, I suppose, just from what we've talked about, is that as you go from phenylalanine to tryptophan, you're increasing the conjugation of the system. So tryptophan has got 2 rings, and phenylalanine has just got 1. So therefore, its lambda max is a bit higher, or it's a lower energy transition because it's a pi to pi star transition. And also, you notice that the absorption coefficient, we didn't cover this that much, the absorption coefficient for the tryptophan is much stronger than the phenylalanine, and that's mainly due to the fact that it's got, again, this NH group. This tends to make the band a bit stronger for the tryptophan. Okay, so we'll leave it there. So I'll see you at the workshop in G54.